Okay, welcome back Year 12s to this second video regarding standard scores or Z scores. In this one I'm going to run you through some examples where we are finding the original score when we're actually given the Z score. And you'll see that we have here a separate little formula, but I will demonstrate exactly where this comes from just to begin with. I might actually move this down so you can see it. There we go. Alright, so here we have the formula that we will use to derive a Z score. So the data value minus the mean divided by the standard deviation. Now, if I rearrange this to make x the subject, so remember x is the data, or x is the original data or score. We call it a score sometimes as well. What I'm going to do now is rearrange this so I can get x as the subject. So my first step is going to be to multiply both sides by the standard deviation S, and finally to get x the subject I'm going to add the mean to both sides. And you'll see I've just rewritten it like this, so I've got the x at the start, and what you've got here is exactly what's in your notes, and this is the formula we're going to use to find the original score. So going back to this point here, an example of a question you might be faced with the original score looks like this. Distribution of scores is normally distributed. We've got a standardized score of 1.7, and then we're given the mean and the standard deviation, because obviously we're not going to be able to work out the original score without that piece of information. Let's calculate the student's original mark on the test. So we're working with the original score is equal to the Z score by the standard deviation plus the mean. So we've got 1.7, which we're multiplying by 5, the standard deviation, and from there we'll add the mean, which was 60. And what we should find is our student received a score of 68.5. Now this is in percentages, so I'm going to say my final answer here. His score is 68.5%. So we're basically substituting the information here into the rule. There's another one here. The mean length of a batch of broom handles is 120 centimetres, and we've got the standard deviation. So mean and standard deviation here. Assuming that the distribution is bell-shaped, therefore normally distributed, let's get the length of a broom with a negative Z score here of 2.2, so negative 2.2. X is ZS plus the mean, therefore negative 2.2 times 3 plus the mean of 120. And we say we get 113.4, therefore the length and that was measured in centimetres. This last question here on this page is an example of comparing different scores, and this is given a range of different information. This is going to bring together some of the percentages from earlier, the 68, 95, 99.7 rule. So we've got two students and they're comparing their results and they're making particular statements to each other, and we're going to investigate whether they're correct. Betty says that she beat more people in chemistry than her friend Sue, and that she got a better score. Sue says, however, that she was in the top 2.5%. This is where our information comes in, which is going to allow us to actually work out who did have the better score. So Betty scored 40 in her chemistry test, and you'll see here that the mean score was 40 as well. So if Betty scored the same as the mean, it means her Z score was 0. We know that about Z scores, that if they're equal to the mean, they are 0. Now this means, if here it says that there are 300 students in the chemistry test. So how many students then did she beat? Here she says she beat more people. So we're going to check if that's actually true. If she scored the mean, it means that she was the 50th percentile. So she actually beat half of the students that sat that test. Means she must have beat 150 students. By beat, we just mean she got a better score. So 50% of them. Now, this was Betty, so I'll just put a B for Betty, and this is for Sue here. Sue scored a Z score of 2. We're given that information here. So this means she's actually in the top 2.5%. So her statement that she was in the top 2.5 here, that's actually correct. Now, it says it had a mean score of 10 and a standard deviation of 5. Okay, so that's, well, we could work out what her actual score is. So mean of 10, standard deviation of 5, and she was 2 above, so she scored 20. So you can see why Betty might think she has a better score. Betty scored, it was up here, 40, and Sue scored 20. But when we look at the Z scores, and that's what we do when we compare results from different distributions, we can see that Sue has in fact scored, in terms of percentages, the better score. We can also have a look at, if we want to, how many people she's actually outdone in terms of the test. It says here that there were 120 students who sat the test. So if she has performed in the top 25, or 2.5%, I should say, it means that 97.5% of students were below her in their achievement, and we can do 97.5% of 120. So this means that she's outdone 117 students. So in that respect, Betty's statement wasn't all incorrect, because in terms of the number of students, she has achieved a better score than more students, so 150 students compared to 117. But as a percentage, Sue's is definitely better. So if we wanted to summarise that, we could say firstly that Betty did, and I'm going to put beat like this because that's the word that she used, Betty did beat more students in her test. $150 compared to 117. However, Sue outperformed, and I do apologise again for my writing because I'm trying to do it quickly. Sue outperformed a greater percentage of her peers. This can be seen from her Z score, because that is what we're using as the comparison of positive 2 compared to Betty's Z score of 0. Okay, so I just wanted to go through maybe one more question, and you'll see that we do have a mixture. Here of a range of normal distribution questions, standard score questions. We mix it up together because this all is part of the same topic, and of course in your exams and your assessments they are going to be mixed up just like this. One more question just so you can see how they look like, what they look like on your end of year exams. So here we have one from a few years ago where they're dealing with two different variables. So they've mentioned here mean and standard deviation of the variables population density, so it's here in the first column, and area for 38 inner suburbs. So this is part of a longer question, so it's just one excerpt from it. Now it says here one of the suburbs has a population density of 3,082, so that's my data value. And here it's asked me for the z-score of that suburb's population density. So be careful here because we want to look at the mean and standard deviation from this column here. There is another column with area, so we want to leave that for now because we're just looking at the population density for now. Okay, so determine the z-score. Z, x minus mean over S. We want to take the x value, which is the data value that's given. We want to subtract the mean, which is 4370. You'll see that we're going to get a negative here, divided by the standard deviation. Now, when you do that, you're going to get negative 0.8, etc. It doesn't, I think it's 0.8256. We're going to round to one decimal place, so negative 0.8. So that's important because it says that right there. So that's for 1 mark on your end of year exam. Next one says, assume the areas of the inner suburbs. So area now, I gave the area, oops, whoa, gone too far. Area is here. Assume that's normally distributed. How many of them are expected? So we're not finding for sure, but we're finding what we expect given that's a normal distribution. How many expect to have an area that's 2 standard deviations or more above the mean? So think about the normal distribution, 2 standard deviations above the mean. I want you to think about what percentage would be in this little tail up this end of the normal distribution. At 1 standard deviation, we've got 16%, and at 2, we've got 2.5% in this section. So we are expecting that 2.5% of the 38 suburbs will have an area 2 standard deviations or more above that mean. Now it says how many. It doesn't say what percentage, how many of them. So what we're going to do then is calculate 2.5% of 38, and we are going to have to round that. And what you should find, because it says here whole number, is that we have 1 suburb. Expect that 1 suburb will have an area 2 standard deviations or more above that mean. Okay, so that's enough now for the examples. From here, what we're going to do is have a go at some individual or independent practice on this, and I do encourage you to send me any emails of any difficulty that you're having, and I'm happy to meet up with you one-on-one if you're finding this part of the topic to be particularly challenging.